to Desk Lady Ada.
Hey everybody, welcome to another Desk Lady Ada. It's me, a Lady Ada, and this is my desk. And with me also is Phil, who is on camera control, and we'll be asking your questions on your behalf from the chat. So if you want to ask live questions, go for it. They will be relayed to me via Philophone. And tonight we're doing another video. We did some Pi 3 hacking yesterday and power monitoring and stuff, so check that out. But tonight I gotta get back into work mode, and what I'm working on is more testers. If you don't like watching me make testers, this show might not be super exciting for you because I do a lot of tester making. But tester making is kind of interesting because you get to kind of explore and understand chips in depth, because you know if you're testing something, you have to understand how it works. So I think this would be interesting to anybody who is curious about AVR programming and high-speed programming and verification and USB testing as well. You can see how we test stuff really, really fast, which is what makes it possible for us to make so much stuff so quickly and get it to you. So without further ado, let's go to the hovercam. Okay, so the board I'm going to be testing is this little board. It's basically like a trinket, but it's with a 32u4. It's a little bit like a Teensy 2.0, but I made a couple changes that made it better for me and the projects I want to do with it. For example, it can work with a Li-Poly backpack. It's got a 5-volt buffer on one of the pins. It's got all the pins broken out. It's got V-high, which is like the high voltage from both of these, good for like neopixels and stuff. And you know, I got the reset button and overall kind of like a size and shape I like. So this is something I'll be making and putting in the store. I'm going to use it for a couple projects. So I designed it, and then I thought, okay, well maybe other people would like it too. And it's got ATMEGA32u4 in it. The stuff that I'm doing applies to all of the chips, but in particular the 32u4, you know, has native USB. And the trinkets, you know, they do USB, but it's bit bang style, and a lot of people wanted a native USB. So, you know, I have to basically program these boards and test them. And the ideal way to test and program is with a standalone tester. And a standalone tester is basically, for me, you know, an Arduino, such an Arduino Zero with a pogo pin bed on top. And then, you know, you fit it on, and maybe you press a button, and then it tests it and it blinks an LED when it's done. And doesn't use a computer, because you know if you have a computer, it's not so bad. You basically hook up like your Atmel ICE or your USB Teen or whatever. You program it, and then maybe you do something over USB, and that works great. But you're not going to be able to do testing as fast. And I find that you're reliant on like the computer and what software is installed, and it's okay. Like I don't mind it, but I prefer to do standalone testers whenever possible. We used to do the Flora with the computer, and I think it would take like a minute and a half to test each Flora. And then when we got to, they were very popular, I designed a standalone tester similar to this, what I'm doing now. And I got it down to, I think, like 25 seconds each. And this is also going to be used for the Circuit Playground, because it's similar chips. So the code I do now is what I'm going to use, is going to be adapted and be similar. So, I do like a standalone tester for a lot of devices, like sensors and stuff. But what's interesting about this is I want to also test the USB interface. And so to test USB interface, you basically want to make sure it enumerates. In my opinion, if it enumerates, it's done. Like it works. Because that means that your data lines are right and your clocking is right and it's precise enough to get enumerated. And I used to use an Arduino Mega ADK, which is an Arduino Mega plus a Max, it was like a 1312 or something USB host chip, basically the USB host shield built into it. But the Mega ADKs are kind of being discontinued, and so I wanted to update the code and design to use an Arduino Zero, which has native USB and a programming interface. So you can program over this one and then still use the USB for native talking, and it's a currently made Arduino. And I like that it's smaller, and it has a ton of RAM and a ton of flash. So the Mega does too, but like this is kind of the next generation. I figured like, okay, I should roll with the times and update my tester code. So I'm going to start by doing it on a breadboard. And I have most of it working, and I'm just going to go through kind of like, I've been hacking on this a little bit, but I'll go through it and I'll show the similar program that I wrote before. So let's go to the computer. So I pulled up the ATMEGA32u4 datasheet, and you don't have to go through this because the code's already written, but what's neat about this chip is it's SPI programmable. Basically, if you send it the right SPI commands with the reset pin held low, with the reset pin held low, you can send it, logic level SPI commands, and the SPI commands will actually do stuff like erase the flash or program in bytes. And it's all discussed in the memory programming area, like it tells you what the signature bytes will. I don't know. Hold on. Sorry, it was memory programming. Yeah, hold on. Tells you the fuses, it tells you signal name, it tells you parallel programming, which we don't do. Let's keep going to serial programming. Where's serial? Serial downloading. Okay, so serial downloading, basically you use clock, data out, data in, and as long as it's clocked and you're doing it slow enough, you can send it into these instructions. So like if you send it this command, chip erase, which is a 4-byte command where these are the first 2 bytes and these don't matter, it'll erase the chip. So, that's how you erase the chip. And then you can start programming, write memory pages, EEPROM. And basically all the AVRs are the same. So this code was written, this was actually adapted from AVR ISP, and then I think someone else made a standalone program. I don't remember, it's been a couple years, but basically I adapted it to be able to program AVR 8-bit processors natively, as long as you can fit the program you want to program into Flash, right? So that's a limit. Like if you have a 32-bit, 32K Arduino Uno, you can fit the Trinket bootloader in, or even the Trinket Pro bootloader, because it's like 2K, but you can't program in like a gigantic amount of Flash. Because you have to fit what you're programming into the Flash, right? So I guess you can use an external SD card, but I basically just upgrade to the Mega, and then you can fit as much space as you want. So this is kind of what we're doing in this program. And then there's like the full instruction set. And then I realize I have a tutorial called Standalone AVR Chip Programmer, and this basically has the code in it. Yeah, this is the tutorial on how to do it, and this is me doing it a while ago. Here you go. So this is it. So this is basically how I program in a ton of bootloaders really, really fast. It's kind of like this, except this is a raw chip, and instead of doing the raw chip, I have the chip soldered in. But basically, now this is not, sorry, wrong tutorial. I have a lot of tutorials. This is the right one. So this program basically stores in it, and you can go through this, it kind of talks about it, and you can download the code, but it basically, you have a CPP file called images, and it's part of the bootloader programmer, and you create a new although I thought image T is actually a constant type. Progmem, held in program memory. Boot image gives you the name, the chip that you're programming, the signature bytes, so what it queries the signature of the chip and then programs it. The pre-program fuses, so sometimes you have to unlock it, and then like you want to set the fuses to a certain frequency or whatever. The post-program fuses, and then the fuse mask, since not all the fuse bits are used. The size of the chip, the size of the bytes per flash page, because like how much you program in before you tell it to write that to flash. And then you actually put in the Intel hex code, like here. And this is actually the program you want to write in. So you just paste in the text. In this case, I have 2 chunks of memory. This chunk up to here. I like to fill out to the end of the page. This is, I think, like the blinking test, and then this is the actual bootloader, which starts at address 7000, so it's like at the end of memory. And this program gets loaded in by code.cpp, which has those commands that you saw in the PDF are basically programmed in here. So, you know what, actually, let me get back to, oh, hold on. Memory programming and then serial downloading. So for example, let's say we want to read the signature of the chip, right? So that's the unique burned in name of the chip. So you send in, first byte is 30, and then you just have to make sure it's 00, and then you can read signature byte, 0 through 4 at address B. So you see here, it's got that SPI transaction where I send 30, 001, so I read the first byte, and then I send 30, 002, read the second byte, and then I concatenate them together into target type, and I basically return it. Or let's say I want to program in the lock fuse. So in this case, write lock fuse. It's AC and then 7, or E, sorry, ACE 0, so this is binary, but then it's converted to hex here. And then you write that fuse byte here. So you can see, like, here's how you do the SPI transaction. Literally, you just send it this command, and then F is the fuse byte, and it writes it. And normally your AVR programmer would be doing this using like AVR dude, which basically just tells it what SPI commands to send. But in this case, you actually do it from within the code. So here's the bootloader programmer. And to make it easy on me, even though it's SPI, I bit bang it. So if you look in the code, when I run SPI transaction, see if I can find that function. It's probably at the very end. Yeah, SPI transaction. You can uncomment this if you want to use hardware SPI, but I actually bit bang it. I just like outset and outclear the pins to bit bang the SPI, and that basically just makes it easier on my tester, because the Arduino Zero is running at 48 megahertz, and the SPI can run like so fast that I don't need, like, the SPI on the Zero runs faster than the 32u4 can accept it anyways. Like, you want to run your programming at about like 4 megahertz or less, and even at that speed, it's like blindingly fast, so much faster than running a program to do it, because you don't have to go through the USB port to like send the SPI commands, that I even have to put in an SPI delay here. I figured this out. I basically have to delay 2 microseconds when programming Flash for every byte, just because it's like so much faster than the program the chip can handle. So basically, you can change these pins around, but let's go to, we can go to quad view or hover cam view, and I'll program this. I'll put this thing together. Bang. Okay, so eventually I'm going to use like pogo pins for this, but for now let's just leave that be. So I want to power this. I'm going to connect the VBAT to 5 volts, and then I'm going to connect ground to ground. So I actually already had this do something, so that's why it's blinking. Normally it would be off. And then clock goes to digital 2. MISO goes to digital 3. And mostly goes to digital 4. And then reset, which you also need, goes to digital 5. So that's what you use to program it. I actually have a little bit more going on here, because in my test program I want to verify that I have the right chip installed, and so I check the regulator to make sure that the voltage is correct. So to do that, I have a voltage divider. So I'm just using two 10Ks. So dividing what the 3 volt line is from the regulator. So it should, if it's a 5 volt regulator by accident, it will give me 2.5 volts. If it's a 3.3 volt, it'll give me 1.65. That's divided by 2. And then I hook that up to A0. So before the Arduino Zero starts programming this chip, it'll check the regulator and make sure it's 3.3 volts. Okay, so let's go back to Compy. Okay, so this is the program, and this is an adapted code. You know, I've written this code multiple times, so it's got a little bit of crust in it. For example, there's NeoPixel, so I use a NeoPixel to tell the person programming like what color, like the color of the LED tells you what's going on. So if it's red, it means it's broken. If it's yellow, it means it's waiting for you to start the test. If it's green, it means test passed. Blue or whatever, like white, means like it's programming, whatever. So there's actually going to be 2 images, but for now I'm only going to do the bootloader image. So what normally I would do is I'd program in the test image, and then the test would run on the chip, like the self-test, and it would output on the hardware serial pins, hey, like test passed, but I'm going to do that later. I don't have time for that now. I'm just going to do the bootloader. So this is an external pointer just to this image here. This one. Actually, what is image T? Because image T should be, you know what, I don't think this is const. Okay, well, we'll see. I'll fix it later if I have to. I have some global variables. I need to keep a page buffer, so this is the size of flash. I don't even know why probably shouldn't even be in this file. It should be in code.cbp, but this is from like forever ago. I keep track of how long I've spent running this program, and then we get back to setup. So setup, all it does is set up the serial console, prints out what it is that I'm doing, give me a couple milliseconds just waiting, and then just stabilize everything and wait. Notice that I kind of need this sometimes, especially if I want to make sure that this gets outputted. In case it crashes later, I put this in to force this to get printed. I might reduce this later to speed it up. I'll reduce it probably to 100 milliamps. And then, again, I don't have the pixels set up, but imagine there's this beautiful LED ring that'll tell people like what the status of the test is. Okay, so start with a loop. I'm going to read the 3 volt logic, that analog read from A0. I'm going to read that, multiply it by 2 because there's a 10K divider, multiply it by 3.3 volts, which is the reference voltage on the 0, divide by 1024 to get me the floating voltage, and then I'll print it out. And basically, like if the voltage is varies too much, return and start the loop over. And this is also another good way to detect whether the board's actually placed. Next, what I like to do is, since there's a lot of pins, I like having it so the chip is put in place, clamped down with a little clamp, and then a button is pressed to start the test. And in this case, I'm having the button be the same as the reset pin, but later on I might add like a big button that you press and it's just like a button. But it's also kind of nice, it lets you use the tactile switches as a way to verify that it's ready to program. You don't have to have another button, and you get to test the mechanical button. So print out, hit the button for next chip, and then wait, while the button, there's a pull up on reset, so wait for that to get pulled low, and then wait for it to be released. Start keeping track of time, set the LEDs to be yellow, which is red plus green, and then start programming. So the first thing you're going to do is I just say like, okay, I'm going to find this thing. Turn off the target power, just check that you have a pull up on reset. So make sure reset is, if it was in some bad state, it's in the right state, especially it should be powered through USB. Turn on target power. This actually isn't really used yet, but eventually what I'm going to do is I'm going to actually turn on and off the, do a hard reset, because some of these chips, especially when you change the fuses, you have to do a hard reset to get them to kick in to whatever you did with the fuses. like a reset isn't enough. You have to do a full power off and power on. Put it into reset by driving the reset low, and so now it's in programming mode. And now you can read the signature. And basically, make sure you have the right chip installed. So if it's got the right chip, I mean, I don't know how that could happen in production, but an ATMEGA32u4 gets put in instead of a 32u4 or whatever, this will fail. It will not continue. And then I have this commented out section because I'm going to do the test program, and then I have to test the test, but I'm skipping ahead to the bootloader image. So I'm going to load, I basically just take the address of the bootloader image, I erase the chip, so wipe it clean, and start programming mode, and I take the pointer to the hex code, which is this gigantic text array, and the page size, which I also read from there, and the chip size, and I basically increment through each page. Start with page address 0. While the page address is smaller than the chip size, read one page worth into give me a buffer, and I guess it goes into the page buffer. I guess it tells me the position. I don't remember exactly what the function does. Check if it's blank. This is a little speed up, so if the page is all Fs, like this is pretty rare, like I usually take those out, but if the page is empty because it's all Fs, I skip it. Otherwise, if it's not blank, I flash it. I say, write that page and then tell the chip to flash that page to memory. And then you just increment by, this gives me the new position for where in the buffer I am. I increment the page buffer, and I continue. So basically just go through and write every single page. And then I write the fuses. And then I flash verify. Verification is a lot faster than flashing because you don't have to do it by page. Verify actually is done byte by byte, it's easier to do than flashing because you just literally read byte by byte. You don't have to do a page at a time because it's not like writing the flash, you're just reading direct from memory. So it's slower because you do it byte by byte, but it's easier because you don't have to do it by page. So a little trade-off. But you have to send like a full SPI command, which is, yeah, so like with program memory, you have to like load the page and then write the page. But when you want to write the memory, read the memory, it's a command, and you just tell it, hey, I want to read from this address, and it just concatenates the address and gives you that byte. So it's like super easy to do. And then I verify the fuse, and then I turn the power off. And then the next step I'm going to do is the USB verify, and this is where I would test that it enumerates. So let's just upload this, and hopefully it will work. It was being finicky, but so I'm now programming the Arduino 0, with the code that will test this. And it's uploading. It's a little bit big, but that's okay. Okay, it took 4 seconds to verify. And then, so open up the serial console. And, can you actually go to computer? Because the computer is a little more. The text is pretty small. So it prints it out. It tells you what the voltage regulator is. Okay, 3.36 volts, good to go. That's okay. Press button. So now it's waiting for you to press the button. So I press the reset button, and it will start program mode. It reads the signature, erases, flashes the boot, and verifies the fuses, and then it's okay. Now it's hung on this USB verify, but as you can tell, like all that while it was printing this out is how long it takes to flash a chip, like super, super fast. Much faster than it would be, like, because it is a full program and verify, it's way faster than it would be if you were using a USB Teeny or even like an ATMEGA32u4. I don't think it would be nearly as fast. But the next step is we want to add the USB verify stage. That's what I'm going to try to do. Do you have any questions while I'm waiting?
No, you're dazzling.
Dazzling.
Yeah.
Okay, so now, so this is like actually recently I did some poking at the USB host code for the Arduino 0 because like it's a little bit under construction. but I did get it into a pretty good state. So this is USB descriptor example. So this is just the example code they have, but I just made it so you could change what debug output you're using. And there's a lot going on here, and it's kind of like, it's like print unc disker, it's like kind of funky. But basically what this does is set up the serial port. Actually, just serial debug begin, start descriptor test, initializes USB, hopefully USB starts, wait 20 milliseconds, and then in the loop, it just waits for, if a device was plugged in, it just prints all of the descriptors for it. And it's just kind of like this mess, but it's okay, we're not gonna need all of it anyways. But it prints up the descriptors and basically what was enumerated. And it lets you know that something enumerated. Again, you know, you should test your device really, really well. And if you have something that's really essential and you want to make sure, like, this absolutely positively has to work at the computer, and they're doing something unusual with USB anyways, connecting to a computer so you make sure it enumerates, and then running the program is fine. In my case, you know, I've kind of like this bootloader, which is basically the Feather Flora bootloader. It's really well known. I've really never had an issue with it. If it enumerates, it works. So I'm not going to test any USB data transfer other than enumeration, because in my opinion, if you enumerate and you get the right VID and the right PID, you're done. So that's good. Okay, so let's go to HoverCam. Okay, so there's two USB ports on the 0. This port is the debug port, and this goes through the EDB chip, the eDebug chip, which we did a 0 debugging tutorial a bit ago. And what's nice about this is that it's completely separate. It actually just uses the serial for the serial. The serial port is a hardware serial that goes through this, so when you press reset, it doesn't like kick the USB. And it also lets me free up this port, which is a USB host capable port. This can be USB client or USB host. So you can plug a keyboard into it, or it can act like a keyboard, right? Like, or you can plug a mouse in and get mouse data, or you can have this act like a mouse. So kind of nice that it can do both. And then I'm going to use this on-the-go adapter from like the Arduino, the Pi 0 with the Arduino 0. So this basically converts this micro USB port to a USB-A. So that's kind of nice. And then I can just plug in a standard micro USB cable into here. And then I'm going to upload, okay, so we can go to computer cam. I'm going to upload this USB descriptor example just to see, like, does it basically work? Okay, and then open up this serial console, and then is this, okay, so there you go, like, it, it initializes a USB host, and it says, okay, I found one device, and it gives you the device descriptor. I'm not going to go into USB descriptors right now. Check out Jan Axelson's site. But basically it says, like, it found vendor ID 2399C. It's actually a typo. It should be 9A. I'll fix that. Gotta remember to fix that later. Hold on. Fix. This has to be have a new. I'm reusing this old Feather bootloader. I'm going to update this later to be a different VID and PID, even though it's the same bootloader. But this is just to test if things basically work. It found the device, it found the descriptors. This is some text that, says like Adafruit or something. Everything basically looks good, like it found this device. So what I'm going to do now is, since the USB enumerated properly, I'm going to add it to the bootloader tester. So I'm going to basically like kind of copy and paste this together. So add USB hub here, USB host. I'll add a new section. And I don't think think I'll need all of this. All this stuff is like printing and stuff. So let's add this USB host stuff at the bottom. So normally it's a USB verify. So here we do like a reset. I set the output low and then high. I will now initialize USB. And then if it fails, like something really bad happened. But you know, I'll return anyways. Actually, I want to use, one second. I have a nice little print status. Okay. Print status, I'll do that instead. Okay. Delay 50 milliseconds and then print. Initializing USB. Take that out. And then changes to say failed. USB host did not start. It's unlikely since it's built in. And then print OK. Waiting enumeration. Okay, and then I'm just going to grab this while one USB task. So you kind of have to run this forever, kind of, and then put this there. Second. While it's running, okay, so it looks like, yeah, USB state running means it finished enumerating. So then I want to get the descriptor. So let's get print all descriptors. Oh man, this is annoying. Is there a way to just get the device? I think I can just do this, no? Right, numconf. Get dev descriptor. Actually, I'm gonna try this again. So instead of just this, I'm going to not print all descriptors, but print descriptors for this address, which I'm going to say is 1. I don't know, we'll find out. So let's try this, and then I'll just copy and paste that text back here. That was not correct. I'll figure out what is correct though. Are there any questions? Question about the descriptor.
Someone wanted advice for someone who's afraid of loops and always finds a way.
Just as it's scared of loops.
Yeah, they're scared of loops.
Loops are scary. So I'll actually clear this. Open this. Looks like this also got to like kind of a bad spot, but all right, maybe I'll just maybe a dev address. print descriptors. What I can do. Hold on, let me do this. I'll figure out what the print all descriptors is supposed to do. Because I don't really want to do a callback. Yuck. Okay, so this print all descriptors. Is this the one? Oh man, what? All descriptors, debug, address. No, it is address 1. That's weird. Okay, well. I need to get the descriptors. Don't really get why this is crashing on me. Well, it's just this. Okay, no. Now, of course, it works fine. Okay, well, I'll just grab this. Sorry, descriptors. Get device descriptor. Because what I really want to do is just get the descriptor. Okay. Go in here. I'm just going to grab this. Print text. Okay. Let's see if I can do this. So, who knows what our code is? Non-conf. I only want 0 and address 1. Don't need I don't want the device descriptor, so print program string. Yeah, this is such weird. Basically, I want this. Okay, I don't even want this code. There's like so much code I'm digging into. Okay, I want to get this. Yeah, because what I really want is to get this buffer here. So let me, I guess our code stands for return code. Oops. Code. Okay, so what I really want to do is just get the device descriptor for address 1. Numconf isn't used, just put it into this buffer. And then all I want to do is just verify that I've got the right vendor ID and product ID. So if our code is 1, turn otherwise. Just try this. Okay, so basically what I'm doing is I don't need to look at the configuration. I don't need like every single thing. All I want to do is enumerate and read the vendor ID. Okay, so let's try programming it. I can also skip the programming step if I want to do it. So USB initialize. Let's see. Plug this in. No. Actually, what I think I'll do is save this as, I'm going to simplify this. This is already like way too complicated. And since it's hanging on initializing USB, I'll figure out what I'm missing. Because I do not need all this stuff. This is totally insane. Like every possible configuration descriptor. Don't need it. So let's go to setup. And let's go to loop. And then USB task. And then I'm going to get rid of this. And I'm just going to do this. So if it's running, I'm going to return this while. Let's see what happens here. And I'll keep hacking on this, but basically just like squish this code together. Let's see, I'll spend another 5 minutes, and then if not, I'll end streaming, but I'll just keep hacking on it, go to sleep. Okay, so this worked. So now I'm going to get rid of all of this stuff. Get rid of this stuff. Don't need that variable. What am I missing? Let's see. USB. Did I have to do a begin? No, there's no begin. Okay, so this is minimal, so that's good. Let me put this up here. Might as well initialize this early. Let's see why this won't just be like exactly the same. Yeah, it's weird. Oh, you know what? I think I'm running out of memory. That's probably what's going on. Okay, I need to do more work. I want to work on, basically, I think when I ported this, I didn't put the image in constant memory. So I have to go back and do that, because right now I'm just crashing on initializing USB, which probably means like I'm at the very limit of RAM, because I've got that gigantic bootloader image stored in RAM. So next step, go back and just get that back into constant memory. I think I was just like playing around with it, so I put it in RAM to make it easy. Put in constant memory so to free up RAM, and then go back and I'll do the USB test, finish initializing USB, and then I'll be able to do program in the bootloader and then reset it and get the enumeration test working. And then after that's done, I'll have like a NeoPixel or something that'll blink green. I'll be like, it's working. Whew. So that's where I'm at. But at least I know what's broken. Okay, hold on. I'm going to fetch Phil. Can you turn off?
What happened?
I'm back. you took a break.
Okay.
I'm done.
Okay.
Sorry. I don't know how to end the stream.
Say night.
Good night. We'll be back tomorrow. I'll finish this up.